welcome back to another week. So at the end of last lecture, we basically looked at how to interpret odometer test data, how to plot void ratio versus effective stress plots. Now, we can perhaps do an example together to put these equations into context, especially how to use them. So let's do that. So in our first example related to consolidation, we are given odometer data, or also known as laboratory consolidation test on the soil specimen. And this soil specimen is likely intact and obtained from the field. You're given the dry mass of the specimen, the height of the specimen at the beginning of the consolidation test as 2.54 centimeters. You know the specific gravity and area of the specimen. And if you look at the table below, you know that there were about 8 loading increments, or 8 points. You can see that initially you have applied no load to the specimen and you have initial height of 2.54 specified in the question. And each time you approximately double the loading on the loading yoke. So, if we want to make use of odometer data, we need to be able to plot void ratio versus logarithmic effective stress plot. I'll explain why we use logarithmic plots later on, instead of simply plotting with sigma prime. So let's do this example together. So based on the series of equations I showed you before, we can calculate the height of solids first. So this equation was taken just about 2 or 3 slides ago. Flip back, we convert weight to mass. Subscript W here refers to water, of course. We know the initial mass of the solids is 128 grams, it's given in the question. We know the area of loading is 30.68 centimeters squared. We are given a specific gravity, and of course we should convert the units that we do care of. And we'll get about 1.52 centimeters. So that's the height of the solids. So if you flip back a few slides, you'll see why we're calculating the height of solids, because we want to calculate the height of voids. And the height of voids is the initial height minus the height of solids. And we could perhaps give this units of centimeters, and we know from the previous slides, if we know the height of our voids over the height of our solids, then we get our void ratio. And this is back to the basic cell mechanics. So we can use all the data from this table here to calculate the height of voids. So we know the initial height was 2.54, and we know the height of solids is 1.52. So if we keep on iterating, then we can get the change in our specimen height. And of course we can calculate our void ratio as well. And as expected, the void ratio should be decreasing. we compress the soil specimen. So I guess that's simple enough, right? And then we can plot our void ratio versus normal effective stress plot as specified. Why I want to go through this is I want you to understand how we get the void ratio versus vertical effective stress plot first, because we need to use it to get our compression coefficients later on in this module. Right, so with that tabulated data, and if you have graph paper, and you can plot void ratio given as V versus vertical effective stress will be in Pascal. So this is logarithmic plot here. We're going up order of magnitude each time. And if you plot the data from the previous table, you should get some curve like this. There should be about 8 data points. And so forth. So this is how we treat odometer test data. So it's nothing complex, so I'm not going to go into detail. Everything will be given on Moodle later anyway. So this is quite simple, right? So what do we care about next? So that's the data. That's pretty accurate. Why do we care? Well, we want to know a few things from this curve. We want to understand whether the soil is normally consolidated or over-consolidated. So what do these terms really mean? Well, there's also a third term at the bottom in red, pre-consolidation pressure. And we can understand most of these features if we plot void ratio versus logarithmic effective stress plot. Now, let's talk about the concept of pre-consolidation pressure first. So we can treat pre-consolidation pressure as some sort of reference point. We can treat it like a memory. At the bottom it says soil has memory just like human beings. Well, yes and no. We often say that the pre-consolidation pressure is like the memory that the soil has. Soil always remembers the most pressure it's experienced in its life. Well, it's just like human beings. If you've experienced a very high stress scenario, maybe having to prepare 3 final exams and also having to do capstone FYP project, that's perhaps the most stress you've experienced in your undergraduate career. So you'll remember this point. And just like soil, if it's experienced the highest stress level, it'll remember that. And just try to recall that that's what we refer to as pre-consolidation pressure. We'll come back to this point and explain what it is, using a few examples. Now, we often refer to 2 types of soil. The soil can be either normally consolidated or over-consolidated. And you can see from the definitions here, normally consolidated is if your soil present effective overburden stress is already the maximum pressure that it's ever experienced, then we say the soil is normally consolidated. In contrast, if the soil is experiencing a stress level that's actually less than what it's encountered in its lifetime, then we say it's over-consolidated. And of course, you can also add other qualifier terms in, like heavily over-consolidated. And there's also a term called under-consolidated as well. What's under-consolidated? Let's say we have an undrained scenario where we can't really transfer a lot of the total stress to the soil skeleton because the pore pressure or the excess pore pressures won't dissipate, right? So in fact, we're applying a load that's much higher than the soil is actually experiencing, right? Because it's undrained. Well, under that circumstance, we can say it's under-consolidated somehow, right? But you rarely see a term like that. It's quite a niche case. But in general, we usually just say normal or over-consolidated. But let's take a look at a few examples. So in terms of finding the pre-consolidation pressure, we can obtain this from what I just showed you, the void ratio versus effective stress plot. And we can do this by graphical approach. So if you see this on assignment or you see this on a final exam, obviously we're not going to ask you something so simple like pre-consolidation pressure because you're supposed to know this from your soil mechanics class anyways, but you can quickly surmise that you could probably use the Casagrande method. And the Casagrande method is actually listed in 5 steps on the slide. Well, the first step you would do is, let's say you have some odometer data like this. What's happening is, well, initially your soil's here, you load it to point C, and then at point C, what's happening? If you recall, you're unloading your soil, and at point D, you stop, and then you reload your soil again. So you can see that this loop, the loading and unloading part, are not the same, and we call this hysteresis, right? Because the loading and unloading curves are different, and this is just due to soil being a natural material. And in most of our theory, we normally assume that, well, just a single slope will suffice, right? So when we load a soil initially at point A, we have some curvature. There's some point here that we want to mark at point B where there's a drastic change in slope. What does the slope mean on an odometer curve? What's the physical meaning of the slope? Well, it sort of means the stiffness of the soil, right? If you think about it, it's reminiscent of the stiffness of the soil. Did we turn off the AC in this room, or is it very stuffy? No. It's probably dangerous these days to have a stuffy classroom. Can someone in the back, or do I have control? If you can see a switch, can you turn it on? To get some airflow in here. Yeah, thank you. Other side, perhaps? Students on the left side, my left side. Is there a panel in the back? We can get some fresh air going. Yeah, if we can, that'd be great. I think it's better for all of us.
I don't think it's the AC.
Oh, it's not the AC, right? Oh, okay. Hope we're okay then. Only 20 more minutes to go, or 30 more minutes. But all right. So where was I before I found it stuffy? Right. So we're talking about this. So this soil in particular, you can see that it followed one type of stiffness. So there's some slope here, and then at some inflection point B, it followed another type of stiffness. And what happened in terms of slope? Well, the slope was quite shallow initially, and then it turned into a much steeper slope. And what does a steep slope mean? Well, a steep slope means that you're applying a bit of effective stress and you're getting a lot of change of void ratio. So it's a softer response, right? The second part of the curve is a softer response. The stiffness is much lower than initially. So we can somehow say that inflection point B, or somewhere around inflection point B, is our pre-consolidation pressure. It's where we reach the point where the soil exceeds the maximum stress that it's ever experienced in its life. And then it becomes quite soft thereafter, right? So inflection point B, if you look at odometer data, even if you go on a log scale at the bottom, it's not easy to find. It's a very weird curve. So how do we get a point? Because any one of us in the room trying to get the pre-consolidation pressure might get a slightly different value. So Casagrande in 1963 came up with a visual observation approach, which is slightly graphical, right? To help you eyeball your pre-consolidation pressure. So we know that if, well, let me explain something else first. Okay, let's say we were loading a soil A until point B. We know that's our pre-consolidation pressure now. And then the soil becomes very soft, and we load it at point C. And then we unload. What happens when we unload? Well, we get, again, a different slope. And notice how this section of the curve looks quite similar to this section, right? So the next time we reload again, what's our pre-consolidation pressure this time? It becomes point C, right? Because the soil has experienced a maximum stress level of point C. Compared to before we loaded it, it was point B. Anyhow, digressed a bit, but back to the main point of Casagrande's method. So if you ever have to get the pre-consolidation pressure, of course you can eyeball it. I don't think it'll be substantially off if you eyeball it, but there are instances where these curves are not as easy as this theoretical classroom example. So the first step is, well, establish point A, which is apparently the point of minimum radius of curvature. And if you're not sure what radius curvature looks like, what's considered a high, large radius curvature, what's a small radius curvature, you can look at this diagram here. And let's say we identify, okay, we think point A has the minimum radius of curvature, and then we can draw a horizontal line from point A to line AB. After that, we draw a line AC, which is said to be tangent to point A. So tangent to point A, it should run tangent here, and then you have line AC. After that, you draw another line to bisect BAC. So BAC, if I use a different color, is right here. Bisected means cut in half. So then you get line AD as the bisector line. So the last step after bisecting this angle of BAC is you draw a straight line that's somehow proportional to the second part of your curve, back to intersect line AD at point F. So we have some sort of line here. And we can then say, look, we have point F, and we extrapolate down the x-axis, and this is our pre-consolidation pressure. So it's not quite at point A. Even this method has a bit of interpretation. I mean, each of us interpreting the point of minimum radius of curvature could be slightly different, but I guess there's some method to this, right? Anyhow, that's how you would eyeball it off of a void ratio versus effective stress plot. We won't talk about it too much because the point is you're supposed to understand this already from soil mechanics. Now, what are some processes that can create over-consolidated soil in the field? Well, it can be natural or unnatural. Let's look at the first example together. The first one is a natural process. Probably hundreds of years, thousands of years, millions of years of geological phenomena, particularly erosion and deposition. So, if we look at the schematic here, what we have is some soil element here, brown part. And if we look at our void ratio versus logarithmic of effective stress, we have point number 1 here. So we're at some initial stress, sigma subscript 1 prime, some void ratio. And let's say we get some deposition. So you can see that initially the surface of the soil is here, but let's say there's a debris flow or some landslide processes that deposit over here, and a million years later you have the added overburden on top. So what's happening with this added overburden? Well, this added overburden will compress the soil. You'll see a void ratio reduction as you compress the soil, and you'll reach point 2. And point 2 is in essence the largest stress that this soil element has ever experienced in its lifetime, because initially it was just experiencing a very small overburden on this side. And now it has a very large thickness of overburden on top of it. So you reach this point, and point 2, if nothing else adds to the stress on top, will become your high stress level experienced by this soil element, making it your, well, pre-consolidation pressure. And it's denoted as prime, sigma prime, subscript C. Okay, so let's say after this, there's a river on top of this, or very strong winds. You have alluvial or fluvial processes that further erode the soil. Well, if you get some erosion, what is erosion? Well, erosion is stress release on the soil. So if you have stress release, what happens? Well, you might get a bit of swelling, a bit of heaving, maybe some elastic release. You might get a slight increase in void ratio, which is what you see here. Not much, but you have some increase in void ratio from the stress release. Same as if we had an excavation, we would see stress release in the soil by removing overburden. And what happens to the effective stress? Well, the effective stress will reduce accordingly. And we can see that point 1 and 3 don't have the same effective stress because at this particular location here, we haven't eroded it to case A where the line is here. So that's essentially a natural process that will give you different pre-consolidation pressures. We can also generate over-consolidated soils using construction or manual meats or man-made synthetic meats. And this is what we do in ground improvement, in reclamation. We often place surcharges on top of soil to improve the soil. So if we focus on the example at the bottom, let me delete some of this. If we look at this example now, so we can simulate this natural erosion and deposition process and use it to our advantage as geotechnical engineers by applying surcharging. And we often do this for reclamation. We may install a bunch of band drains or PVD drains inside a layer clay and dump a very heavy amount of fill material on top to provide a surcharge. And what's happening? Well, so again, we'll try to explain this process using the void ratio versus sigma prime logarithmic plot. So initially you have a soil element here. We call this sigma prime subscript 1. And then we throw a bunch of soil on top. Engineering fill, sand, it can be anything you like. It can be a bunch of concrete blocks too. Some total stress on top. And what happens after that? Well, you'll see that when you put a surcharge on top, so initially we're at this stress state here. We apply a heavy surcharge and we'll increase the effective stress and we'll also compress the soil. When we compress the soil, the void ratio will, of course, decrease. And that's where we move along this line to stress point 2. And again, let's say stress point 2 is the high stress that we'll ever encounter because we're not going to apply any more surcharge because we're going to remove the surcharge afterwards. Well, what's happened? Well, let's look at this. So we apply surcharge from 1 to 2 and we get a reduction in void ratio. So we've in essence reduced the compression of the soil. And we can view this as consolidation, right? So we've compressed the soil so we'll have less settlement later on. Now, after we release the load, we'll get rebound, right? Just like the case of natural erosion above. When you remove the load, you'll get stress release. Effective stress will decrease. You'll get a bit of swelling in the soil. Now, why do we do surcharging in the field? Look at the slopes here. So we have slope, let's call this slope A, and we'll call this slope B. What did I say the slope was? I said it's reminiscent of the stiffness of the soil, right? So if you're an engineer, you want to apply some sort of loading here. let's say after step 2, you want to build some, I don't know, some home or something on top, okay? So as an engineer, do you want to build on slope A or slope B? Of course you would say slope B, because it's much stiffer. Stiffer as in you won't get as much compression and settlement in the ground. So I hope this example shows you how it's similar to erosion, but more importantly, it shows you the power of surcharging. If you surcharge a ground, you'll get a much stiffer response the second time you put some infrastructure on it. And a stiffer response means less compression, less settlement of your infrastructure. And no one really wants to deal with settlement, right? You don't want your railway track to settle, for example. If you want to build utilities on it, you don't want your pipelines to settle. So this is one method of ground improvement, surcharging. It's quite simple, right? Throw some load on it and remove it, and your soil is magically stiffer. We'll talk about how to do the calculations for surcharging later, after we finish the consolidation module. So these are examples of how you can generate over-consolidated soil. Of course, these are the points where your soil will be over-consolidated because it's the maximum stress level encountered in both cases. Now, alternatively, you can also have what we call climate loading on the soil as a natural process. Now, there is a caveat though. We have to assume that this loading is somewhat rapid and it does cause consolidation. If it doesn't cause consolidation, you're not going to get any volume change. And this graph is not going to make sense. So let's simplify it and assume, yeah, there is volume change because this soil consolidates. Maybe it's the first time it's experienced this rapid increase in generation of excess pore pressures. So with that in mind, let's say we have the wet season on the slope. You have quite a high water table relative to this soil element. So you're somewhere here. You have some effective stress, sigma, prime, naught. And then in the winter season, the groundwater table will recede or decrease. And we know that with the reduce in pore pressure, we get increased effective stress. And let's say this is the first time the slope has experienced it, and we generated quite a bit of excess pore pressure initially on this natural slope, okay? And then we get increase in effective stress, and you get substantial void ratio change, which is probably not so realistic, but just let's make a few assumptions here. You get void ratio change, and then after that, you have the summer season again, and this time your slope is less vulnerable to substantial changes in void ratio. Wetting will, let's say, the soil is still relatively impervious, you generate excess pore pressures, and you get a reduction in effective stress. And let's say the water table is magically at the same level as step 1. Then you'll have the same effective stress as sigma prime naught, and you'll get a slight increase due to if you treat it as an unloading process. This is highly idealized. Probably not the best example, but we just want to stress that climate loading can perhaps affect your soil as well. And we can see that climate loading can create, although extremely exaggerated, some sort of pre-consolidation pressure in your soil, just by fluctuating the groundwater table. Now, in a similar manner, using synthetic means, let's say we sink a dewatering well in the ground on a construction site, and we want to draw down the groundwater table because we're building an excavation or building a cofferdam or something, right? So let's say this is the initial groundwater table in the ground, this is our soil element, and this is very similar to wetting and drilling. We turn on dewatering pump, and we draw down the groundwater table. And after we do that, let's say the pump turns off, and then the groundwater table goes up again. And this process, although it doesn't go back up to the initial surface, there's still a bit of difference. So we have the initial effective stress. When you draw down, you have an increase in effective stress, and when you have an increase in groundwater table, you get a slight increase in effective stress, decrease in effective stress, but you get a slight increase in void ratio. So these two top and bottom cases are synonymous with natural and synthetic means, and you can imagine that climate loading by changing the groundwater table can perhaps have some implications on the pre-consolidation pressure. That's why when we're on construction sites, for those of you that worked on sites in the summer as an intern, sometimes when we have dewatering wells, so when you have a cofferdam, so this is a sheet pile wall, and you have, let's say the groundwater table's here, your groundwater table here, and let's say we have some buildings and railways here, okay? What we're worried about when we draw the groundwater table down, let's say the groundwater table is also high in your excavation. So what we want to do typically is draw this groundwater table down to here so we can get machines inside to do construction. When you draw this down, what's going to happen? Well, you're going to form seepage, right? The water's going to go this way, and then this water table is going to come down as well. When this water table comes down, we might see consolidation outside, right? If it hasn't happened substantially. What happens when you consolidate soil outside a cofferdam? Well, you might see this infrastructure wanting to settle. So we have to account for these things when we do a sensitive impact assessment for our construction site, when we draw down the water table. And that's particularly why we're talking about this case and how you can actually create over-consolidated soils just by drawing the water table down. But of course, this is not so easy to understand because you're not sure what your soil has been subjected to on site in the past. So what we here have very idealized cases here. And anyhow, so these are situations how you can get over-consolidated soils. Now, how do we describe over-consolidated soils? You might remember from your soil mechanics class that we use something called OCR. This is the over-consolidation ratio. And how do we calculate the over-consolidation ratio? Well, we know what pre-consolidation pressure is now, right? And we just divide that by the current stress level that the soil is experiencing, or the current effective stress. And we can use this ratio to define whether a soil is normally consolidated or over-consolidated. So if your soil right now is experiencing the maximum stress that it's ever experienced, then you'll have an OCR of 1, right? It's normally consolidated because these two numbers are actually the same value. But if your soil level is much lower than your pre-consolidation pressure, then you have over-consolidated soil. And can you have an OCR less than 1? Well, theoretically you could, right? As what we talked about, you could. If the soil's undrained, right? Let's say the pore fluid carries most of the load. Before it becomes drained, technically your soil has experienced a higher load, so OCR could be less than 1. We can call it under-consolidated if we want. But not very mainstream, as I mentioned. So that's what we use, OCR ratio, to characterize over or normally consolidated. So why do we use logarithmic plot? Well, if you look at this graph here, the x-axis is not logarithmic, and you'll see that the curves are, well, quite curvy, not quite linear, right? When we do a logarithmic plot, we can really spread the data out. We can get a nice linear curve, and we can treat it as a single slope using a linear equation, y equals mx plus b, right? But if you don't, this is how the data would look like. But let's take a look at this example together. So we have 3 soil specimens, or 3, well, it could be the same soil specimens, sorry, but different stress levels. So in our usual manner, we have void ratio versus effective stress, but not logarithmic. So initial stress state is here. It's about 100 kPa if you go down to the x-axis, and we load the soil to 200 kPa, and subscript C means this is our pre-consolidation pressure, And if you unload the soil, so at point A, this would be the maximum pressure your soil's ever experienced. Okay, so that's your pre-consolidation pressure. So that's why OCR is 1. If we unload to stress point B, what's our effective stress level now? Effective stress level is 100, but what's your pre-consolidation? Your pre-consolidation is still 200, right? So at point B, if you calculate the OCR, 200 over 100, then you get an OCR ratio of OCR 2. If you further unload the soil to stress level point C, which is 50 kPa, then you'll get an OCR 4. And this is perhaps a heavily over-consolidated soil. And if you want to reload the soil, there's a bit of hysteresis. And you keep on loading it, then the soil becomes normally consolidated again. And we call this line the NCR line, so normally consolidated line. Or it's also referred to as the virgin compression line in textbooks, because it's the first time that the soil is experiencing these stress levels. Now, the hysteresis is interesting. When you plot this onto a logarithmic plot, it really straightens everything out, and you can probably idealize the hysteresis with a single slope. It's probably not as consequential. So here's just an example of 3 different stress levels for OCR. So let's work on another example together to slowly get out of this consolidation module. So what you see here is just a quick application of Casagrande's procedure. So you're given void ratios and effective stress, particularly given 6 data points. So you're just asked to find the pre-consolidation pressure. Obviously, your assignment and your exam will not be this easy, but you have to do this anyways. So we just followed the procedure in the last slide, right? First of all, you find the minimum point of radius of curvature, and then you draw a line horizontally from AB, as we talked about. After that, you draw a line tangential, and then you draw a bisector. And the bisector will hit the point F, and you bring it down, and you get pre-consolidation pressure. So we're not going to go into this in detail because I think it's quite simple. And just use this procedure if you're given a graph and you have to get the pre-consolidation pressure. So here our pre-consolidation pressure is 160 kPa. Now, okay, simple enough, but let's look at the differences when we carry out a logarithmic versus a non-logarithmic plot. So on the left side, you see that we just plot void ratio versus vertical effective stress. On the right side, we have void ratio versus the logarithmic of vertical effective stress. And we know as scientists and engineers, anytime we have a log versus log plot, you'll get a linear relationship, right? But in this case, we're only logging the x-axis here. So you can see that this is our NCR line, normal consolidation line, NCL line. This is the loading unloading curve. Anything on the NCL line is virgin compression. Anything to the right of NCL line is not feasible or possible state. So your stress level should be on the line, because it's the maximum stress level in your counter, it's the virgin compression line, or you can have an unloading stress level to the left of the NCL line. And if we do a logarithmic plot, what do we see? Well, it becomes a lot easier to apply theory because we've linearized everything, right? So when we linearize everything, we don't have a nice curve here anymore. And we don't have a lot of effect from hysteresis from loading and unloading. If you look at this graph now, if we throw in a logarithmic plot, what happens? Well, everything becomes very straight. Your NCL line, your normal consolidation line, becomes really straight, and you can characterize it using a single slope. So C subscript C is our compression index, right? And then you have your secondary slope, your unloading slope, C subscript S. And likewise, you also have impossible states on the right side of the NCL line. And notice how that the hysteresis is not so important anymore, and you can probably just use one line to get the slope of this curve. So when we calculate or predict how much settlement we get and rate questions, we often adopt compression coefficients and compression indices. And like I said, what these compression indices mean in terms of physical meaning is the stiffness of the soil. Stiffness during virgin compression and stiffness during unloading. So let's look at how we can calculate some of these compression indices together. So to do this, the next step we have to do is, so far we've basically looked at how to look at odometer data, and we did it extremely fast because you should understand already. The next step is, well, what's the predicted settlement? Right? We need to know this for ground improvement because we need to know how much soil fill we need, how much sand we need. Let's say you have a clay layer that's 10 meters thick. After consolidation, it becomes, let's say 1 meter. You can calculate it. And then you know you have 9 meters times your area of sand replacement fill that you need. And it can be quite expensive. And then you might think to yourself, maybe I don't want to compress this so much. Maybe I'll put in some deep cement mixing columns. So I don't get compression. I don't need so much sand, right? So it really depends on how much compression and how much replacement you can handle. So again, this should be somehow a review type material, but how do we calculate settlement or how much compression to expect from a one-dimensional element? So let's take a look at the schematic here. We have an initial soil element here, and in this element we have soil, we have voids, and we have solid. So void and solid will comprise soil, and what you see on this picture is a conglomerate or mixture of both voids and solid. And we know the typical cross-sectional area is, let's say, A. We have initial height H, and let's say we get some compression or settlement. We can call it variable S. Our initial volume is just the height times the cross-sectional area, is V naught. And after some change in volume or settlement, we'll get a reduced volume from compression. So if we break this schematic diagram up, we can, just like in our odometer equations, put all the solids at the bottom and put all the voids at the top. So that's exactly what we're doing here. So our solids are here, and the voids are up here. And the total height should still be H. We still have settlement S, but we've dissected this into volume of solids, volume of voids initially, volume of voids after compression. Because with compression, the only thing that's changing is your voids, right? You're not really compressing your solid elements, right? So based on this schematic diagram, we could calculate the change in volume under some average overburden effective stress. And we can see that the change of volume is your initial volume minus your change in volume, V1. That's delta V. And V naught is what we talked about, H times your cross-sectional area, and V1 is H minus S times cross-sectional area A. So this is basic relationships, right? And if you simplify that, you'll get relationship settlement times A is equal to your change in volume. So that's easy enough to understand. The next step we have to consider is the change in total volume is equal to the change in volume of the voids. So again, we know from the above derivation that change in volume is S times A, and we know that from this relationship here that any change in volume in voids initially minus the incremental change will give you this relationship here. Again, this is easy enough to understand. So the next step we have to look at is how do we define void ratio? Well, void ratio is given as your volume of voids over volume of solids, and we looked at that already. So we also have to pull up some mass volume relationships from our earlier classes, and we can deduce that the volume of voids is equal to the initial volume over 1 plus E naught. And you can simplify this expression, and you can probably work through these very simple relationships later on your own accord. And if you break this down further, it becomes quite simple. We know that change in V is SA, and we know the change in void ratio here times Vs is also your change in void ratio, which is equivalent to your change in volume, and we know that the change in solids is this times your void ratio. And then we can simplify everything in terms of S, and you can calculate your settlement based on void ratios and initial heights. So all you need to know is what's the change in void ratio, what's the initial void ratio, and what's the initial height of the specimen. So that's how we calculate settlement for this particular element at the top. That's not what we're interested in though. We're just doing this so you have all this on paper, so you're not confused. What we're interested in is how do we predict how much settlement there will be after primary consolidation. So to do that, remember that I mentioned everything is on a log plot now because we want to linearize everything. So the subsequent approaches to estimate settlement is really based on void ratio versus logarithmic effective stress plot. And it's as simple as a linear equation, y equals mx plus b. So the void ratio is more or less your y, right? And then you have some slope times an increment in your slope, and you can calculate the change in height. So in the case of normally consolidated soils, we move down the NCL line, right? So which index are we interested in? We're interested in CC, right? If you look at this relationship, we're interested in CC. If you want to predict how much settlement you have along this line, then we use the CC compression index. And if we do that and we rearrange some equations, then you'll get this formula here. And this is really nothing complex. This is just a linear equation substituting basic mass volume relationships. So on your own accord, this week, you can try to derive this once. And without these slides, you can probably do it. And you'll arrive at this equation here. And you can use this equation at the bottom in the yellow box to predict how much settlement from the NCL line alone. Now, we know that sometimes we unload the soil and we need to calculate the settlement resulting from unloading and reloading as well. Well, it's more or less done in the same manner, right? You just have to change the index. It's the same thing. If you want to look at CS instead, the swell index. So CS is replacing CC in this case. So if you look at this equation, it looks quite long, but it's actually not that complicated because it's just describing, basically, if I delete some of these scribbles, it's describing this linear line here if you use CC, and it's describing this linear line here if you use CS. If you don't believe me, you can try to derive these tomorrow. So anyhow, so you get two expressions to characterize your swelling line and your compression line. And if you do the same manipulations, you'll get a separate expression with CS instead of CC. So now that you have both expressions, you can, well, calculate settlement for everything on an E versus effective stress plot. You can have other preconditions as well. If your sigma prime initial is plus your change in effective stress is larger than your pre-consolidation pressure, then you have to account for compression and swelling. And in that case, you would just add the two lines together, and again, it's a linear relationship. And please try to derive these again on your own time, because we're out of time here. And we'll do some examples together next class. So I'll see you on Friday.